आपको जाना है क्या?
हाँ पॉसिबल हो तो
शेयर स्टॉक शेयरिंग
पॉसिबल है।
होगी।
सुन क्लेंसर नहीं है। It's working, but then just a minute.
How to look for
Just let me.
Hello, yeah, hello everyone. Today we are going to present on the topic of visual attribution. So I am Madhav and this is Karan. Let's start the presentation. What's our basic problem in visual attribution is that the current computer vision and the deep learning models have problems in identifying the particular regions of the image which have led to that particular classification of that image. For example, as you can see in this case, the input image of the cat, what exactly, which parts of the image is exactly led it to the model to predict that it is a cat is the major concern of our now. And the current challenges in these methods are that there are like inaccurate small regions which lead to misleading correct attributions. So even if the input image is predicted correctly as cat, but the attribution map may sometimes not depict the most important sub-regions of the image which have led to that prediction. Also, in case of incorrect predictions, we are not able to gauge while exactly a certain model has predicted that class inaccurately, what all features or what all parts of that image has led to that incorrect prediction. So, we are going to present this paper. The first paper is less is more, fewer interpretable regions by submodular subset selection. It was in ICLR 2024. So the key idea of this paper was that it reformulates the visual attribution problem as a submodular subset selection problem. So the basic idea, what the paper wants to achieve is that we have to select a fewer but more meaningful and impactful regions from those images, which can lead to a correct prediction of that particular class. So it uses the submodular function to optimize region selection, which is based on multiple characters that we discussed. So it mainly uses a submodular function, which we have to maximize, which is like a combination of all these four evaluation matrices, like the confidence, the effectiveness, the consistency, and the collaboration. So confidence is basically how well that particular region or that particular prediction has aligns with the actual class of that the actual prediction of that model. Effectiveness is that we have to ensure that all the patches which are included in that attribution algorithm, they are very distinct from each other, and there is no common information or there is no semantic similarity which leads to redundancy as such. Consistency is like it maintains a semantic coherence between the predicted variable and the target feature. So if the predicted region patch which is important is either linked to the target variable or is very far away from that target variable. So this is ensured by consistency. Collaboration is like it evaluates the collective region impact. Like there might be some patches which individually might not contribute that enough, but when they are clubbed together in a to form a particular subregion, their impact might affect the prediction. So this is the submodular function we use. So it is a combination of the confidence, the effectiveness, the consistency, and the collaboration scores. So let's talk about each of these scores in details. The purpose of this confidence score is to measure the certainty of the model's prediction, which ensures that we only take the in distribution samples and avoid the out of distribution samples from this. Uh, so it uses evidential debugging. It's submodular. So, so the confidence we have, it like increases as we increase the number of patches in the image. So it keeps on increasing.
Doesn't have this amount.
Right. Yeah, so it will like saturate at a particular point. So confidence is basically whenever we have, it's like each of the class has a particular confidence. So we have to sum up over each of these classes and then calculate this confidence. So it is like calculated using uncertainty. So
It's fine.
right.
Some of it.
Yeah, it's a sum of
Is it genuinely a set value function? Or is it just a set value function pretending to be set value, whereas it's actually a sum of the function evaluations on points?
yeah, it's a pretending, but it's just a sum of over all the entity.
And does that hold with all the other functions?
So the effective, consistency is the dot product kind of thing. So if we move on to the next slide. So the effectiveness score is basically a minimum distance between two features, like two patches of the image. So it like whenever the distance is less than a certain threshold, then we have to eliminate either I or J there. We only keep one of the patches of this image. So yeah, this is
This is also a pretentious set function or actually a set function?
it's a it's a set function because yeah, it like takes into account a particular set of features like which needs to be taken into account.
Said
Right.
collectively they will help. So how they will help? I mean, one patch will be near ESA, one patch will be here.
So collectively, I mean the patches which are like nearby to each other. For example, if we take a certain portion of the ear, but if we don't take the whole patch which has the whole image of the ear, like two, three patches combining will form an ear. So if we take only one of the patches, it may not be semantically good. But if we take all the three patches together, then it might give a good semantic thing that it is an ear. So that's so whole like three patches together can give a good information as compared to single if I take all these three individually. So the consistency score that told is that we have a feature extractor. So we have a patent feature extractor and it takes the dot product between the targeted feature and the feature extractor vector of each of the subregions. So IM here denotes the subregions which we have divided in the image, and it takes a dot product kind of thing, which like is a cos theta angle, if we say, and finally it is the collaboration score is basically as I told that individual regions may be weak, but together they can have an impact on the final prediction model. So this is the form. Consistent score is not.
Does it decompose as a sum of the consistency of the individual points?
So it doesn't decompose as a like it only accounts for like
Point wise.
point wise. So we take 2 points and then
Yeah, but
see
if
the
you look at some of our work, our target substance selection, there's a way you can actually make it genuinely set value.
okay.
Even the target, they are trying to condition, right? Condition of the target. If you condition the target and still we are information theoretic, there is information theoretic functions like information.
Right.
It can be
So this is the correlation. So the major difference is
Dr. Vishak.
that from the whole image we subtract that particular region and then take the dot product and do the further calculation. So let's go to the algorithm, how exactly the algorithm works. So we have an input image. We divide that input image into n cross n patches. Then we apply an already existing attribution algorithm like HSIC attribution of grade K plus plus to get a saliency map, attribution map A, which is shown there. Then instead of like randomly like taking the subregions in line, we allot the subregions in such a way that like this subregion, for example, all these subregions are found. For example, if we have n cross n patches and we want to make m subregions, so each of the subregions would be allocated d patches. That allocation would be based on the importance which we get from the saliency map. So the first, for example, this patch would get the first d important patches. This next subregion will get next d and so on. So when we have the final element set b, we then go on to maximize the submodular function. So with each of the patches, we try to each of the subregions, we try to add the subregion which leads to a maximum increase in the submodular function. So sequentially, we try and select first one, which is the most important, then the next one, then the next one. So we can set a limit k, like how many subregions we want in total, and combining all these selection set, we can form a particular set of the image, which is the most important part of the image. And this is how the algorithm goes. So if you see the graph of the original attribution map, which is generated, even after recognition of like 90% of the image, the recognition score is quite less, which is like after 90%, it is reaching 0.9. But if we talk about this submodular subset selection method, the even after recognition of like 30% of the image, the score has gone up to around 85%. So that's like we can like minimize the number of regions and increase the importance of that of those particular regions to get the correct prediction. So this is the algorithm which I have just now explained. So we can like select how many regions, sub regions we want. We can go up to total m sub regions as well. Next. So this is the mathematical formulation of the algorithm. First, we have to go about making the subsets which are described to get an element set B, and then we apply that greedy algorithm to get the most important K subsets to make the final selection set. So now we come to the experimental results. So they use three data set. Two were the phase data set, cellular and VGG phase 2, and one was the fine gate, the bird data set, CUV 200 2011. So how do they evaluate this result? So they used two scores, insertion AMC score and deletion AMC scores. Insertion AMC scores is basically how much has the insertion score increased when we add a particular region to that particular subregion to the image, and deletion. So deletion AUC is how has the model confidence dropped when we drop the most important subregion. So the key performance gains is you can see that the correct predictions has improved the deletion and insertion score over HSIC attribution, and the incorrect prediction the highest confidence is increased, and the 18.4% better insertion scores are there. So you can see in this image that the HSIC attribution didn't take into account the peak of the bird, which might be a important patch to take into account which class the bird belongs to. But the method proposed in the paper takes into account this, which has I think led to great increase in the recognition score as well. Similarly, for the incorrectly classified as well, the whole of the head of the bird has been included in the attribution patches, which has led to like we can know the reason why the particular bird has been classified wrong. So I will hand over. So I conclude as well, like this paper has reformulated visual attribution as a submodular subset selection problem, and it has led to higher interpretability with fewer dense regions. It works effectively with the face recognition dataset and the bird dataset, and it enhances like the interpretability of both the correct and the incorrect model predictions. It has outperformed state-of-the-art method, which is HSIC attribution and red and faithfulness interpretability.
So, good afternoon, everyone. My name is Suraj Budi, and I'm going to present a paper named the multi-level attribution for vision transformers. So, the paper title is multi-level attribution for vision transformers. So, vision transformers will be has been treated as a black box. So, there are multiple attribution techniques that have been proposed. So, the majorly categorized in two parts. One is internal based, like attention based attribution techniques or graded based attention techniques. The other techniques are attribution based. So we'll come to the attribution based techniques that take input features
Perturbation.
attribution techniques. So in attribution, there are two insertion and deletion tests that we can know. So insertion is basically adding the patches. So what transformers do is divide the image into patches and then provide each patch as a token. And then take the order of the token and then perform the classification based on the transformer architecture. So the insertion and deletion test, what they do, they gradually add or delete the patches from the images and then recalculate the model response. So next thing. So there are some terminology that I want. Yes. So there are some terminology that is first is MR model response, basically the output of the model that we are attributing. Second is density response, basically the amount of image that has been shown till now to the model. Next. The other is alignment currently that has been defining this. That is equal to the model response minus the density, the amount of image shown. So this is the difference between them. Cumulative sum of the differences between them. And the last is magnitude away score that we'll see later. And this is the MRE, which is basically taking the model response for the insertion test and model response for the deletion test. We are putting 1 minus because while creating the model response for deletion, we have reverse the ordering. So that is why there is 1 minus. So the motivation for MDA is basically what previously in insertion, well, previously graded or attention-based attribution techniques will do. They create attribution and then they are being tested on the insertion and deletion test. So the MDA, what it does, it takes the test and try to evaluate the attribution, try to get the attribution based on the test only. So this is it has been done in two stages. First is patch order optimization and patch magnitude optimization. So we'll see the architecture. So as you can see, as I already told, the image is being divided into patches. Then we have we feed the images and then we start from for insertion. We started with the blur image and then we gradually add a patch and calculate the score. And we add the patch greedily. Only the patches that mostly significantly improve the model response. We'll add them. And we'll stop when the model response reaches 90%. Because but after that, for the remaining patches, we started with a black image and started minimizing. We'll go to the next step. So if you can see, the patches are first being added, and we are basically maximizing this thing. So we are basically maximizing the model response So PK is the image at K iteration and Xi is the new value that has been added. So we are trying to get the Xi that maximize this. So that gives an order to those patches. So previously the order was a sequential order, but what we are doing, we are creating order that are based on insertion and deletion significance. Yeah, it is productivity.
Is anything known? Do they talk of any property of the order response function? If they are directly, this is like an algorithm they are presenting.
Yeah.
Not here to solve one problem. If there is no overarching objective that they are presenting.
So basically, they are what they are doing is they are getting a better attribution. They are getting better when we go to the result. They are getting smaller set of patches that are significantly important, and also they are getting better attribution selection.
I understand. See that what I do is one process growing.
Yeah.
The first case maximize model response. The other is shrinking.
Yeah.
And also the other.
Other way there is minimizing the response.
Yeah. And
So that is basically these exercises are these are patches that have the least significance on the.
so they can be removed.
Yeah, so they, can you go back to previous slides?
So what I'm saying is this implicitly they are trying to maximize the environment.
Hmm.
But one is growing from empty side, the other is shrinking from the complete side. But the connection between what they supposedly are trying to achieve, maximize the amount of response, and these two algorithms, I mean, or these flavors, I mean, of course, they will be using something more heuristics to combine insertion and
Yes,
deletion.
that is, I'm getting it. Thinking both things together.
What I'm looking for is there some overarching objective? Like, in this course, what we can do is formulate an objective function.
Yeah.
Overall objective. Is there any such objective?
Yes, sir. We are during the patch magnitude optimization. First, we are getting the order of the patches using this. Why we are getting the magnitude? We are getting a AD, that is attribution, directed attribution. So it is basically a linear regression. Like we do in linear regression, we try to create a.
So this is all pre-processing. So that means there is some greedy approach before the actual optimization.
Yeah. So we go to the next slide. So this is a pseudo code for this. So that I highlighted this thing. Like first we started with the blurred image, and till our confidence didn't reach 90%, we keep on adding the patches while maximizing the model response with each patch, and then for the remaining patches we get our temporary order for and then reverse it and only add the further most significant patches. So this is the patch magnitude optimization that I was talking about. So in this, we first take the mean of both insertion and deletion curves, and then we try to. So this is our mean optimization problem. To get a AD, AD is a curve, AD is a attribution curve that is closest to this mean response. Why we cannot use the actual mean, because it might have it will have ties for it, patches. Attribution school can tie, and it also have not smooth attribution differences. So there are two constraints. So we need to solve this optimization problem, but we have two constraints over it. First is the curve should be when we adding initially when we adding some patches, the response response changes should be larger, and its division is different properly basically. So as we go above the patches, the response delta response is decreasing. So that is strictly decreasing increment, and this is the attribution. This is the attribution we get, and what we did to make it strictly decreasing is just adding a term here, kind of a extra added error or something. Can you go to the next slide? So this is the magnitude.
Min-max for
Yes, sir.
you have AD to be maximized and what you do.
No, so we are trying to get AD. So in this, no, sir, we already have we already generated MRB, That what we call a pre-processing. Pre-processing.
But AD,
AD is a curve that we want. See, we have insertion curve, we have a deletion curve. Then we take a mean of those curves. Then in that curve, there in next. So in that, so this is not mean, but what happens is it is not smooth and it has lines. So what we are trying to do to get a response curve that shows the exact thing, but still has the diminishing return property as well as the continuous addition to the attribution. Next. So these are the steps. So first we calculate the attribution score based on the insertion and deletion test, the mean and the things I have explained. So in this paper, we also include a hyperparameter that is gamma. So it basically gives us a power over the attribution to choose from. So we can go for a sparse attribution or a dense attribution. So sparse attribution means like only the most significant patterns that are required for the classification will be shown, and the dense will be. And so this is the final attribution score. So it is 1 minus gamma A first, and so the important thing is this K. That is the threshold we have set. How much attribution score it should be allowed to add it to the entire final attribution. So as you can see that this is this input of a different image. So if we use gamma equals to 0, though it shows only the important significant patches, but as we make changes to the gamma, we can get a better attribution maps for the for images of like this. And what we have seen that for 5,000 images on 5,000 images, so it GradCam in by attribution, it outperforms all of them with a good margin in both insertion and deletion cases. So and the also thing, one more thing is that the attribution quality when we use the dense thing. So the attribution is very much better segmented. I'll say the heat maps are better understandable. So the insertion score, the MDA will be getting like 8.5, 85% of, and the alternative is still lagging behind. So, but we also introduce our insertion deletion trade-off while introducing the parameter gamma. But that is like we did it intentionally to get better attribution. So the basic advantages of the MDA methodology is the tests that are used to determine the score of attribution or the quality of attribution is being used to create the attribution, and we also have a flexible. We can choose from a flexible attribution method, and the limitation is just that it is computationally expensive. But we have been doing 3 kind of optimization in between. So and if the patch level resolution is not good, so the attribution can show very funny results. There's also I like to introduce a paper that is Bayesian. So this is just an introduction and we carry. So this is it is not an optimization paper, but it is a Bayesian paper for uncertainty quantification. So what it does, so the basic intuition behind it is like whenever we feed an image to some neural network, it gets some parameters in it. So we didn't do anything with the parameters till now. So what they have proposed what they have proposed is it takes a set of parameters as a Gaussian as a distribution. Here it is taking like Gaussian distribution, and the Gaussian distribution we get from the base, like opening the base theorem for the, and here theta is the parameter and d is the entire test. So I'll hand it to So we are trying to incorporate this in our submodular function.
That's your.
Yeah, so we'll show the results like some of the experiment we have done. Experiment, yeah.
Just we like the uncertainty confidence thing that I described in the lesson more paper. We try to modify that uncertainty estimation by incorporating certain uncertainties, which were derived from this Bayesian paper, like Laplace approximation, which was based on the Bayesian uncertainty. And we try to model it, like try to add this uncertainty and see how the model has performed better, or is it like moving towards a model function. So
This is not made. This paper.
no, yeah. So this has like the original uncertainty which are described in the lesson more paper, and apart from it, it has the things which were described in the Bayesian paper. So entropic variation regulation, Laplace uncertainty, which is based on the Bayesian-based confidence measure, and the PFP uncertainty, which basically measure the uncertainty figure.
The target.
That they have done. Okay. Why don't you do that? This part is fine.
So this part was explained.
I'm just saying, not important. They got it.
Just the results of this part, like just it has the original SMDL and SMO paper had this one, but I showed a like slight improvement, not much improvement. But we are trying to like improve on this or like try some different.
The other one targets.
Yeah, they are coming.
And we'll see the authors again.
Sure, sure.
You have to switch the device. Okay.